house to myself, so I've just been like doing math. I spent all Saturday just on the couch watching horror films and working permutations out, just like, it's glorious with my pugs piled on top of me. Just the best. Okay, so let's actually do a quick recap of a few things that will help. I've just written up some facts here that I want to just start off with a mention of. So last time, essentially last time and the day before roughly. So we had S sub n, which is what? Is this like my final and differential and whatever?
Except the like group of permutation group, right? Of like n permutations.
That's pretty of n items,
Or,
right?
okay.
On a set, on the set 1 through n.
Right?
Right, so this is equal to the set of all permutations on the set x equals 1. Cool. Is this a group? This is a group. The identity is E, that just the transposition that leaves everything alone. We call it epsilon, right? We use Greek letters for these guys. We also saw that any sigma in SM can be written as a product of disjoint cycles. And that's what your homework in part was about, product of disjoint cycles. Oh, I just remembered, I got a cool handout I gotta remember to get to you. And Christian, there was a question you asked me that I want to talk about as well. We know that if sigma and tau are in Sn, then they commute if what? Do you remember the condition?
They're disjoint.
Disjoint, yes. Sigma and tau are disjoint. In other words, they don't share any common references. You don't see a 3 in one and a 3 in the other. They don't touch any of the same elements. But Christian, you asked me a question. You're like, but wait a minute. So Christian's question was this. We had something like 2,5 and 5,2. We had a transposition. And Christian said, well, wait, these commute, right? 5,2 and 2. Oh, wait, do they commute? Let's see. 2 goes to 5, 5 goes to 2. I guess they don't commute, actually. Oh, that's right. But this commutes with itself. What the hell was the thing? What was the thing? What was it you were asking me about? Because so there was something with some transpositions commuting. And the thing about this is that every transposition is its own inverse. Now I'm starting to forget what I thought I had in mind what the question was.
I think it was something about like there being like an if and a, like it was originally phrased as a biconditional.
Yes.
Right.
Yes.
And it's not a biconditional.
It's not a biconditional. But the reason it's not a biconditional is because in these transpositions, they are their own inverse. So they always commute. That because the example was like that we were talking about was something with a transposition. So the only time you could move away from the only time you could share an element is when you have a transposition and its inverse together, because this is actually just 2, 5 as well, and everything commutes with its inverse. So I don't know. On the couch, watching Blair Witch Project, this all seemed like it was completely relevant, but yeah. So I guess the one thing I wanted to say is other things commute in here, Christian, but they have to be inverses of each other. Oh, that's what I wanted to say. Yeah. So if I have a tau and it's actually sigma inverse, then this definitely happens. And these will share elements, but it's because, that's what I wanted to say.
Okay.
Because inverses always commute.
So you don't need disjointedness to have commutativity.
Yes.
If you have disjointedness, you are guaranteed commutativity.
Absolutely.
Okay.
But there are circumstances where you will get commutativity even if they're not disjoint. Yes.
Yes, yeah, but in that case, you have like some sort of inverse transposition.
And I think that's the only time. I think they have to be inverses to commute otherwise. That's it. Okay, so anyway, I have a bunch of stuff written down. Felt a lot cooler about it than this feels right now. So let's move on. What else did I want to say? Oh yeah, and then I want to kind of prove some things, but first I got one last one. Every sigma in S sub n, every permutation, can be written as a product of transpositions. And just to quickly remind you of how that works. You can pick any element and pivot from that. What you want to do is work from the furthest one. So watch this. I can do this as 1, 2, 1, 7, and this was something else I learned, so I'll show you this. 1, 3, and that product of transpositions is this guy. But you can also pick a different linchpin. You just need to be careful and remember that this is a wraparound. So if I wanted to start at the 3, the furthest thing from the 3 this way is actually the 1. And then I go 3, 2. And then I go 3, 7. And I think that works out. Let's check out. Let's see if that works. I know this one will work, but let's do this. So first off, trying to recreate that. 1 goes to 3. 3 goes to 7. 7 never gets touched again. 7 goes to 3, which then goes back to 2, and we get back my original. So if I wanted to pin this on the 7, how would that go? 7 what?
3.
7, 3, the furthest, you have 7, 1, 7, 2. And that'll get me the same thing. Let me stop. Does that sound okay? Sophie, yes?
Where does the 7 go?
I'm sorry.
Oh, 7 goes to 3, 3 goes to 2.
Yes, yes.
Sorry.
Yeah, it's okay. You good?
Yeah.
You feel okay about that? Cool.
Yeah.
So notice that I've actually done this multiple ways, and it's always got 3 transpositions. So this thing is always odd. No matter how I broke it down into transpositions, I got an odd number. And that's what I want to show, is that this number of transpositions that you can write everything is well defined. It's invariant, no matter how you do it. So we have this theorem. Let me formalize what I'm saying here as opposed to babbling. Here we go. Here you are, buddy. So this is actually theorem 5.5 in our book. We need a little lemma here first. I'm going to kind of breeze away the lemma with some kind of soft words. Lemma, if the identity is the product of these transpositions, B sub k, where beta sub I is a transposition, however you spell transposition, there we go. And another word for transposition is 2-cycle. You could call it that. You could call this a 4-cycle. You can just some other language, just the period of the thing, the number of elements in it, dash cycle is a good name for a permutation. So if this is true, what do you think has to be true about k? Does it have to be even or odd? Does it matter?
Is it K is like dependent on 1 less than the size of
It is, well, so E is nothing, right? I know how you're thinking. So if you're thinking here, we had a 4 cycle and it was
Yeah.
3 transpositions. That's not quite where we're thinking now, because this guy here is the identity.
Oh,
So it's a little bit, and that has 0 cycles. That's a 0 cycle thing. So what do you think has to happen if I'm constantly, if I've got a bunch of things, if I've got a bunch of things and I start swapping them, how many times do I have to do that to get everything back to where it was? Even or odd number of times?
even.
Has to be even, because if I move something, I have to put it back at some point. So every transposition needs to eventually be undone by another transposition. So this K is even. And that's the thing I'm not going to prove. But if you think about how transpositions work, it kind of, did you have a?
Is that because of the whole 2 cycles?
Yes, yes.
So then if it was 3, then would it be on or?
No, then it would be uncertain.
Oh.
These transpositions have a very special just place. Yeah. That sound okay? Yeah. Cool. This is a lemma, so that means a theorem's coming up that uses this, right? Lemma's a little building block. Proof? I just proved it by moving things. Good enough. All right. You seem well convinced. So wonderful. Theorem. What I want to show is that when I take a permutation and break it into a product of transpositions, that is unique. So if sigma is a transposition on n things, and sigma equals alpha 1 through times, these are prime times alpha sub n, and sigma equals beta. Let me just get my notes because I'm just about to want to make sure. Yeah, we might have a different number here. Beta 1 through beta sub m. So if I take a permutation and I do that decomposition into transpositions, so this is where alpha I and beta j are transpositions. Then m and n are either both odd or both even. Then m and n are either both odd or both even. And a way to say this, a really elegant way, is that the parity of a permutation is invariant of its decomposition into 2 cycles. That's a super fancy fucking way to say it. I'm going to write that out. I.e., the decomposition, or the parity, even or odd, of a permutation is invariant of the decomposition into 2 cycles. That, another way to say that, a higher level mathy way, is that i.e. parity, this idea of even and odd transpositions, is well defined. And that's a good math word. Now, well defined in math means this statement holds true no matter what representation of the thing that I have. So really lovely proof, and it's going to hinge on that lemma super quick. I'm trying to avoid, I'm making sure we don't go into the dustiest and most painful of the proofs. This is a good one. And so proof. Suppose alpha equals, what did I do? Did I say alpha, or sigma, sorry, sigma equals alpha 1, alpha 2, alpha n, sigma also equals beta 1, beta 2, through beta m, where the alphas and the betas are transpositions. 2 cycles. That means that this must equal this. The product of the alphas must equal the product of the betas. So alpha 1, alpha 2 through alpha n equals beta 1, beta 2 through beta sub m. Any suggestions on what I can do? Look at the lemma. We want to use that lemma. How can I make this somehow get me closer to that lemma? How do I get an epsilon in here? How do I get an identity into this equation that I have on the board?
They are equivalent, and so one of them can be the inverse. Or is that not doable?
Well, the inverse does come into play. Let's like, how can we move more slow? Let's think more elementary. We're not like, their inverses would be the same, I agree. But how can I use inverses to force an epsilon into this?
You can left multiply or right multiply, so you could like left multiply to each of them their inverse, and then they cancel out on one side, and then on the other side it has both of them.
Yeah, so that idea, we're gonna peel these off of one side one at a time by applying inverses. So the first thing I'm gonna do, let's try to mimic this and get the epsilon on the left. I'm going to left multiply by alpha. Let's do a few steps. So left multiply by alpha 1 inverse. And what you get is alpha 2 through alpha sub m equals alpha 1 inverse beta 1 through beta sub m. And continue peeling off the next alpha. So I'm going to multiply by alpha 2 inverse next on the left, and then alpha 3, one at a time, peeling them off. Continuing, you get, eventually you're going to get epsilon over here, and you'll have alpha n inverse, alpha n minus 1 inverse, alpha 2 inverse, alpha 1 inverse, then beta 1 through beta sub m. Let me stop. Tell me if that makes sense. See how I'm just peeling them off? I don't know if the sound effect helps. Probably not. Let me stop and make sure that. Should I explain a little slower? I'm happy to. You tell me what you need. No, you good on that?
So I'm just making sure the reason
Yes,
why we're
good.
doing n minus 1, like that's where I'm getting lost as well.
Oh, okay, so, the one right before this looks like that. So when I peel these things off, so first the alpha 1 inverse goes over.
Oh, okay. So will it always be backwards? Like,
Yes.
okay.
Yes, and so I was just inserted this guy because he's the second to last to come over here,
Mm-hmm.
and then this guy will come over the end. Does that make sense?
Yeah, but it just to make sure it always goes from, like, if we're saying this side is equal to this side, when we're doing the left multiply by the inverse, it's gonna go backwards on
Yes,
the other
ma'am.
side? Okay.
Yes. I thought there might have been a question. I'm a good brow diviner. Any other questions on this? What do I know about the number of things on the right?
It's gotta be even.
It's gotta be even.
So it's n plus m is equal to like 2k for some integer k.
Yeah, exactly. Exactly. So this must be even because I've got epsilon here by the lemma. So the number of things here, n plus m, is even. What happens if you add an even and an odd? It's odd. You get an odd and an odd, even, even and even, even. So the only way this can be true is that if M and N are both even or both odd. Cool proof, simple. One, if you believe the lemma. The lemma may not be that much fun to prove. This seems way too easy. Somebody suffered along the way, it was the lemma. All right, let's see what else I got. Where's my note page? Oh, I've got shit spread everywhere. All right. So, I think that's all I want to say about that. This is important because it says that every permutation you get can be broken down into an even product of transpositions or an odd product. So every transposition is either even or odd, and that doesn't matter how you do it. You can't go wrong. So this idea of evenness and oddness is well defined. And from that, we can, let's just write that up here. So every permutation, sigma and S sub n, is either even, it's a product of even transpositions, or odd, it's a product of an odd number of transpositions. The even ones, oh, what do you think? Is this even or odd? It's even, because it's like nothing gets moved. 0 things gets moved, 0 is even. There's 0 transpositions here. So just make a note, epsilon is even. And how could I prove that? Let's just see. So epsilon is 1, 2 times 1, 2. That's the inverse of itself. I just wrote it as 2 things, and I know that any way I do it, it's got to be even. I could add on this, but that's a whole different thing. I better do another one and undo it, right? So no matter how I write the identity, I have to undo what I've done. So it'll always be an even product of transpositions. And literally, that previous result that I had up here, I think that oh no, this result right here, I guess this basically says epsilon is even, that every decomposition of it is even. So that guy right there, note epsilon is even. So what we get is that S sub n breaks into even permutations and odd permutations. So it partitions this into 2 sets, 2 disjoint sets. They don't share anything in common. But this one does have epsilon in it. So if anything, if either of these were hoping to be a subgroup,
Only the even one can be.
only the even one can be, because you've got to have the identity in there. So this one here, in fact, we're going to prove this, the even ones, this forms a subgroup. It's a quick proof. We're just going to kind of breeze through it. A subgroup, and it has a specific name, A sub n. This is called the alternating group. The alternating, I think we can call it a group unto itself, of permutations. And I'll tell you why it's called that on n things. It's actually called that because the study of these permutations came from the study of multivariate polynomials. So back when people were studying polynomials like this, x1 minus x3, x2 minus x4. So this is a polynomial in 3 variables, or 4 variables, right here. Polynomial in 1, 2, 3, 4. you don't really need to know this, but I just learned this over the weekend, so I had to share it with you, that when you study these polynomials, when you transpose any two variables, the sign over here does not change. That's called an alternating, wait, hold on. Fuck. It's been a while. Let me look up what I wrote here. Maybe I didn't even write it down. No, I must have written this down. Oh yeah, here it is. So an alternating polynomial does change sign. Poly in x1 through xn change is called is one which changes sign, SIGN, when we transpose two variables.
And what do we, use to, like, write an alternating polynomial? Like, what is it, notated by?
Generally, it's just any polynomial in multivariate, so like even this guy right here, Sophie, like that would be a multivariate polynomial. I just wrote it out in nice factored form so we could look at it. But notice that if I change x1 and x2, does that change the sign here? If I swap x1 and x2, not at all. It just kind of changes those. But if I change x2 and x4, that will switch the sign of this guy right here. But an alternating polynomial, it has to be true for no matter which two variables you switch. So I think I might have an example written out here. Yeah, like this guy. So this is not alternating. And let me show you why. Because P of x1, x2, x3, x4 is not equal to minus P of x1, x4, x3, x2. So what I did was I swapped these two variables, but it didn't change the sign of it. Whereas, but this polynomial, it's called Q of x1, x2, x3, x4 equals x1 minus x2 or x3 minus x4. Is that alternating? Maybe not. Maybe we have to have like everybody in there. Let's see. So do we need an x1 minus x3? I wrote this down as an example of an alternating polynomial, but I don't think I believe it anymore. Because if I change x2 and x3, if I exchange x1 and x2, that changes the sign. If I exchange x3 and x4, that changes the sign. Maybe I also need, what do we need to get this thing to switch? Do you even see what I'm talking about, or am I just babbling up here at the board? Maybe.
I don't really know what's going on.
Yeah, okay, fair enough. I wish I hadn't done this at all, but here we are. Here we freaking are. Let's look at a simpler one so I can show you what I mean. So let's say I've got P of x1, x2. Let's just do 3 variables. I think I got a little too excited. Times x2 minus x3. And now I think I have every combo of things. Yeah. So this here, okay, so look at this. Now if I swap the variables, if I say, let's look at P of x2, x1, x3, that means I'm gonna swap these two right here. That's x2 minus x1, x2 minus x3, right? Because, yep, and then this becomes x1 minus x3. Oh, yeah. So look, that's the same, this one is reversed. So this is actually negative P of X1, X2, X3. I think I don't want to say much more about that. But I think that guy is odd. And that if you switch any two, it will change the sign of one of these things in here in the product. This is so not, I've wasted enough of our time on it. That's where it comes from. If you want to know more, Google it. Because we're not going to spend another second talking about it. Let me give you a handout.
People on Stack Overflow have.
What's that, Sophie?
I'm sure the people on Stack Overflow have an explanation for it.
Absolutely, they do. Don't go to Reddit.
No.
Don't ever go to Reddit.
Don't use ChatGPT.
Oh my.
Steal it from Reddit.
Yes. Yeah, I love it when it gives you these authoritative summaries that came from like.
One
It
guy, we
literally
got
takes
3
you Reddit.
upvotes 7 years ago.
Yeah. It actually, no, it like
One
actually
Reddit
takes
user
from
said
Reddit,
yes.
Wikipedia, I think Facebook. It uses those as its actual sources.
There's no staples in this. That's confusing me. Let's take a look at something.
Good thing I have a stable stapler.
I know. Could you?
Good for it.
Thank you. Get one to come out too, please. Nice. This is my wife's paper. She's out of town. I used her printer.
This is like really fancy paper. Wait, are you?
I know, this is like what a lawyer uses. And then I use it for like stuff I end up not even using.
Is there only one page?
Yes.
Oh. I thought you
Yeah.
said there were, you said you didn't staple it.
Yeah, I thought I had stapled it. I don't know what I was thinking.
Oh, I understand.
It looks like there's a staple,
I understand.
right?
Yeah, it does.
That's what threw me off. So the group A4 is all the even permutations on 4 things. And that turns out to be a very interesting geometric thing. I just wanted to point it out to you and show you a lovely Cayley table, but it is the symmetries of a tetrahedron. And you can see that's all laid out there. Just take a few minutes. Actually, I have to go pee. Would you mind just enjoying, your algebra people, enjoy that Cayley table for a minute. I'll be right back. It's kind of cool. And then we can talk about it if you want. Cool. What a bunch of awesome nerds looking at that table for so long. That's awesome. My people. And notice that that is not all, how many, what is the order of that A4? What'd you say, I'm sorry? 12, right? What's the order of S4? 24, yes. Remember how that works? The order of S sub n is n factorial. So this is exactly half the elements of S4, which is big. Like the Cayley table for S4 would be gargantuan. But here we just have the alternating group, which doesn't always have a beautiful geometric interpretation, but here it definitely does. It's that group of symmetries. Notice the haviness here. And what I wanna prove, actually, is the theorem that says, so what does the theorem say? What's the nice wording for it? Yeah, okay, here, we'll just go ahead for it. A sub n, I'm gonna make a new one. A new is a subgroup of S sub n, and the order of A sub n is n factorial over 2. That, we're not gonna do much with that Cayley table, so don't worry. It's like, I didn't have time to study the Cayley table, totally cool. We'll probably not mention it much more.
Is this still assuming that A sub n is the alternating group?
It'd always be for us, yes, yes, absolutely. So, yeah, A sub n equals set of all even sigma in S sub n. Let's do a proof. Let's show the subgroup part first, and then I'll show you a really cool proof that it's exactly half of S sub n. So proof, first show A sub n is a subgroup of S sub n. What do I need to show? Identity. Are we good on that? Is that in there? Yeah, right? That's the lowest even thing we can think of. Epsilon is an element of A sub n because epsilon is even. Cool, what else do I have to show? Inverses and closure, and I'm good. And the associativity comes from the associativity that composition of transpositions has. So that associativity comes from just composition of functions. That's an associative action. So we're using the subgroup test. Let's do inverses. So maybe you can help me out with this. Inverses, let's say sigma is an element of A sub n. How do I argue that sigma inverse is in there? And start first principles. What does it mean to be an A sub n? You're even. Even?
Isn't the inverse still just the same number of things, so it's still just even?
Yeah, and we're just gonna make that formal, exactly, yeah. So inverses, since sigma is an element of, take sigma in A sub n, so that sigma equals, and I'm just gonna give you some notational help here. Tau 2, I like using tau for transpositions because T and all that, not because I'm T, but transpositions are. T sub R. Let's give R some love. And R is even. What does sigma inverse look like?
It's just T to the R inverse, all the way down to T to the 1 inverse.
Yeah, thank you, Sophie. Get that order switch, right? But as Abraham said, there still are things there. We don't change the number of things. And we know that this decomposition is unique. Still are transpositions, and we can't change the parity of this. This is, if this is even, which it is, there's no other way to write it. So this is even as well. So even. Just pretty shitty little proof, not great. Could add more words, make it nice. If you did it, I would totally not let you get away with that. So we got that, and then closure. How's closure gonna work? How do you think closure's gonna work? Take a minute. Do the closure proof yourself. Think that through. Now that you see how the thought process is going to go. I'll give you a little sanity check on the start. This is probably the only way to really start, to not be in hell of some kind, I would think. This looking good. So how does the rest of this go?
R plus S elements, R plus S is even.
Exactly. So the product is the product of these the hard part is just setting yourself up for success. If you write these decompositions, tau is even number of transpositions, mu is an even number of transpositions, different numbers of, except that even and even is the only commonality. And so then mu sigma is tau 1, tau r, times tau 1 prime, tau s prime. You know, your notation is no doubt different, but there are r plus s transpositions here, 2 cycles, and r and s even implies r plus s is even. And once you're even, that's invariant. You can't write that as a product of an odd number of transpositions. You can write it as a different number of transpositions, but that's still got to be an even number. Thus, sigma is an a sub n, and we see that a sub n is a subgroup of s sub n. still have another thing to prove. Let me stop and make sure everybody feels cool about that.
You said associativity was just given by like composition.
Yeah, because they're literally functions, right? A permutation is a function, very simple function. So now I need to show that the alternating group is exactly half of the set of full permutations. So to see that the order of A sub n is the order of S sub n over 2. Let me make a little note here. Note that that is the order of S sub n over 2. I'm going to set up a mapping between things in A sub n and everything else. So between the even and the odd transpositions, or even and odd permutations. Let's construct a bijection between A sub n and S sub n minus A sub n. So let's actually call that O sub n for the odds. That's a minus sign. This is set. Here I'm using set minus, so take that out. Take that out of there. And here's how we're going to do it. So define, first off, let sigma be any odd, no, actually, let sigma be a transposition. That's not, no, yeah, that's not epsilon. Let it be, and put in here odd. So it's just one thing. So in particular, let's just say if I could, sigma's 1, 2, and n is bigger than 2. So yeah, if n is not big, let's just say n is bigger than 2, then I'm safe. If n is 2, there's not much happening here, and if n is 1, there's even less. So I'm going to say sigma just flips 1 and 2. Is that even or odd? Odd, because there's only one transposition, so note this is odd. And I'm going to define this map phi that goes from the evens to the odds. And this is going to be a 1-to-1 and onto map, and it's simple the way I'm going to define it. You take a mu from A sub n, so mu is an element of A sub n, and define phi of mu to be sigma mu. And Christian, this is exactly what I was thinking about in our conversation today. So notice what happens here. This guy is even, the input is even. I toss on an extra transposition, so an odd comes out. Even in, odd out. Essentially, and if I put an odd in, an even would come out. It changes the parity of whatever comes in. You're just adding on an extra permutation, an extra transposition. So this phi is 1-to-1 and onto. Exclamation point, because that's cool. Let's prove it. So phi is 1-to-1. I'm going to do a little subproof. I'm going to assume that phi of kappa is equal to phi of, oh, let's do phi of alpha is phi of beta. Why, I don't know why I'm moving so high up into the Greek letters. I think I wanted to just make it kappa. So what does that mean? What do I need to show from this assumption?
The beta is the only output that alpha produces, and that like no two same inputs point to beta.
Yes, I want to show that these have to be the same input. That the only way you can get the same output is with the same input. So I'm going to show that alpha has to equal beta. This is the easy way to do one-to-one-ness in general. The contrapositive, where you assume these aren't equal and show that's not equal, so much harder, so much better to work with equality. So from here, this means, thus, let's see, what did I do? So that's sigma alpha equals sigma beta. How do I show alpha equals beta?
Well, sigma equals sigma, right?
Sigma does equal sigma. I think you're, yes?
So like.
Left multiply, but sigma also equals sigma what? Inverse. So it's its own inverse, right? So note, sigma equals sigma inverse, because it's a 2-cycle. So I'm gonna left multiply by sigma. I'm just gonna write sigma inverse, left mult by, well, hell, let's just do it by sigma. And show that we're super fancy like that. And this is the identity, this is the identity, so we get alpha equals beta. Pretty straightforward. And then we got one last thing to show, and that is that it's onto, and I'm going to set you up and I want you to take this home. So I'm going to get you rolling on the onto proof. Phi is onto the odds. So take, what letter should I use? What Greek letter for an odd? What do you want to use? I already used sigma.
You wanted to use kappa before. We'll just go-
Okay. My kappa's. Use psi. I could use, yeah, let's use, I haven't done it. Psi. Oh, see, kasi.
What the hell? Can you please give a slow-mo?
Give you what?
What is that?
That is anything you want it to be. But that's I think it's spelled with this, or maybe it's a K.
How do we,
I don't know.
It's like an
is there like an actual way to draw that? Or
Oh.
is that just,
Yeah.
wait, for real? No way.
So just a scribble is that one.
Yes,
Okay.
that's why it's my favorite. So don't worry about the deeds. Have fun with it. It's like a fee that's tripping. Kind
Is
of.
that like an actual notation?
Yeah. Look up, listen, if you've got a phone, look up the Greek letter kasi. It's either KSI or CSI. It might be KSI, actually. I was thinking Greek. Kasi.
It's XI.
Oh, it's XI, is it? Oh, okay.
There's like 3 different ways that it's drawn.
They all look
It's
like
just
this.
a scribble.
Yeah, it's just a scribble.
It is really just a scribble.
It is, isn't it?
Yeah.
There you go. So this, oh, thanks for the spelling though. I haven't thought about how you spell it. I just say it all the time.
Yeah.
See. The best Greek letter of all. Did y'all ever have that Dr. Seuss book, Beyond Zebra?
Not that one.
Not that one? Because they've got a whole book of crazy letters past this could fit in there.
Oh, I was a Dr. Seuss fan.
Yeah, me too. Especially that book. That book is awesome. Take kasi in O sub n. So now remember, our phi goes like this. A sub n to O sub n. We're going to take our kasi over here, and we're going to find something that hits it. We need to construct the thing that hits it and show that it is even. So, solving phi of sigma equals kasi, I need to find sigma. So let's just put a little note here. We need to find sigma and show it's even. So I go to that nice definition. Oh wait, use mu. I'm sorry, I forgot sigma was part of the definition here. Use mu. Sorry, we need to find mu. Because phi is multiplication by sigma. So i.e. sigma mu equals c. I don't think any of my C's look the same. And that's good. Yeah, maybe not. There might be a little, there's some similarities. How do I solve this for mu?
C divided by sigma.
Yeah, but we don't divide, right? But so you're right idea. Left multiplied by sigma inverse.
Right.
Yes, you're right though. That's exactly the idea. So left multiply by
Or sigma because we're cool.
that's right. Or yes, by sigma. Because I like that, because we're cool, for one, and sigma squared is the identity. So what I get here is sigma mu equals sigma c, sigma squared mu equals sigma c, and mu then is sigma c. Why is this even?
Oh, because C is odd, and so is sigma. So
Yeah.
like, it's gotta be even. 'cause
That's
it's
right, y'all see? So, yes. Penelope?
Because of over here when we used it? Okay.
Yes, because this is just this is one transposition. It's just 1, 2, I guess was what we said it was. And this is odd. So this is an odd number of transpositions times one more bumps you to even. So this is even, so sigma c, which is mu, is even because sigma and c are both odd. And odd plus odd equals even. So that's that's the hard part. Now at this point, what we've shown is the following. We have a one-to-one correspondence between these things, which we're going to call ON, and these things, which are AN. We have a one-to-one there's exactly as many of these as there are of these. For each one of these, there is exactly one of these. We've tied them together with our phi map. So we have a one-to-one correspondence. And because of that, so like, how does this even work? Like, think about it. You take your most basic thing over here, epsilon. That's, oh wait, epsilon lives over here. And then phi is actually going this way, right? Over here, I get 1, 2 epsilon, or sigma epsilon, whatever it was. So that's my lowest thing in this set over here. It's the image of the identity over here. And then for everybody that's over here that's even, I'm just gonna tack on that 1, 2. So it's everything over here is 1, 2 times an even.
Is the direct sum of O sub n and A sub n S sub n?
We don't have direct sums here. Because if we're in a linear space, then yes, that would be the case. The union of those two is S sub n. So that we can definitely say that AN union ON is absolutely SN, 100%. In fact, I do want to say that because there's as many of these as there are of these, so the order of A sub n is equal to the order of O sub n. And this is, let's just make a little note, this is a disjoint union. They don't share anything in common. Nothing odd can be even, nothing even can be odd. So these partition S sub n into these two sets. So the order of S sub n is the order of A sub n plus the order of O sub n, but they're equal. So it's twice the order of A sub n, and now divide by 2. So S sub n over 2 is the order of A sub n. And that's what we wanted to show. Exactly half. Whew. I kind of want to have some fun. Sophie, what was that? There's an expression.
Oh, I was thinking because I can't see.
Oh, okay, cool. Okay, it wasn't that I said let's have fun. Okay, good. That doesn't
No,
sound like
I
you at
actually
all.
just have vision issues.
Oh,
Yeah.
really?
Yeah.
It's okay. We don't have to. It's like,
No,
you know.
sitting closer doesn't fix it, so it's just.
I wasn't gonna say that. I have had people who are like, they sit in the back and they're always like, they come and tell me at the end of the semester, I couldn't see anything. And I'm like,
Okay, sit closer.
bruh.
Yeah, no,
Bro.
I would have fixed it.
Yeah, I would think so. I would think so. I have double vision, and really, sitting closer kind of definitely does help that.
My eyes just fight each other. So.
Really, you don't have diplopia,
I
do
do.
you?
I didn't know if you knew what that was. I do.
I have it.
Yeah.
Do you have prisms?
Yeah.
Oh man. Oh man. Give me a hug. Give me a hug. Thanks. Oh, God, that's so good. You're the first person.
Yeah.
I've
It's
never
not
met
common.
anyone else
No.
who has it. It sucks.
It's weird. You like go to the doctor and say you can't see, and then they up your prescription and you still can't see. And you're like, that doesn't fix it.
Yeah.
Yeah.
Have you tried vision therapy?
She told me I needed to.
Me too, and it sucks. I couldn't do it. It was a lot of, it was like took forever, and it didn't
Yeah.
feel like it was working. Anyway, nobody else gives a shit about any of this. So we'll talk later. I want to start something at least for Wednesday, because I think this might be part of what we finish up on Wednesday, and it's fun. So we're all hanging out at my couch on Saturday afternoon. We're like sitting around watching horror films. I make popcorn. Right? Get used to soda, whatever you want. We don't have a lot of soda, so I bring beer instead. So,
Wait, but what's the beer of choice?
what beer would you like?
Oh.
Have some IPAs. Got some sweet shit. My wife drinks. I can't
Sweet
stomach.
beer.
Yeah, she likes it's like this, like I don't know what it is. Some
no.
marshmallow chocolate beer. Or some god awful.
I feel like that defeats the purpose of
Yeah,
beer.
no, I like beer that tastes terrible. Yes, that's what I want. But it's not terrible, right?
It
It's
is good.
beautiful. Tastes like flowers. All right. So I want to come back to this. So first off, just a couple of notes. Note, S3, how many things are in S3?
Wait.
6.
6. There's 6 things in there. Yep. How many things are in D3? Do you remember that? That's the symmetries of a triangle. So what do we have? We had the 3 rotations. And how many flips did we have? 3 flips. Right, we had 3 flips. And so we had 6 things all together in there. Or wait, maybe did we only have 2 flips? Could be like,
Didn't we have the identity too? So
yeah, we have the identity too. I think you're right, Camilla. Yeah. We have 6 things. Yeah, you were right. I heard you say the 2. So here, the order of D3 is also 6. If you look at the Cayley table we made, which I think we made, it had 6 things in it. So these are actually the same. Remember how we viewed this as a permutation of the vertices? Do you remember that? Now let me just kind of quickly refresh your memory on that. I don't need that. I need that. 1, 2, 3. So if we had a rotation, that would be the permutation that takes 1 to 2, 2 to 3, and then 3 back to 1. So that would be rotation clockwise. by 120. And then rho squared, let's just do it with what we know. 1 goes to where on the squaring? 3, skip ahead, right? 2 goes to 2 goes to
Wait,
1.
two.
Oh wait, 3 goes where? 3 goes to 2, and then 2 goes back to 1, yeah. So there's rho squared, which sends 1 to 3, 2 to 1, and 3 to 2, which is 2 clicks. Cool. And then we also had the identity, which you can write like that. That was no rotations. And then we had these transpositions. Oh, maybe we did have 3 transpositions. Yeah, that's right, that's right. Somebody's gotta be the identity though, right? We gotta have some identity. So one of the flips, if this is tau 1, what does that look like here? What does tau 1 look like if it's a flip over that line?
Over which line?
This
The one on the 3?
guy.
Oh, that guy, oh.
That's just this transposition, right? Leaves the 1 fixed. And then, let's call that tau 1, let's call this tau 2. Tau 2, let's say that's tau 2. What does tau 2 do?
1, 2.
Just flips 1, 2. And then tau 3 is the other guy, what's he gonna do?
1, 3.
1, 3. Cool. So we got our 6 elements, and we can view them as permutations. And this makes it so much easier to compute. Oh my God, if I click twice, and then, remember, it goes this way, and then I do a flip over tau 2, what's the result? Oh, the computations are so beautiful. That's 1, 2, I don't even have to think about the geometry. 1, 3, 2, and what does that turn into? Let's see, 1 goes to 3, 3 goes to 2 to 1, that's it. 2 gets fixed. So it's actually what? Tau 3. And in this way, we could crank out an awesome Cayley table with a lot less work and pain than last time. So when I say that S3 and D3 are essentially the same, these are all the ways you can permute 3 things. You either flip 2 of them or you cycle. And there's 2 ways to cycle them. Right there. So I want to talk about SD4, actually. Because in D4, this is the symmetries of a square. And that is a proper subgroup of S4. But it's not like the table that I gave you on the tetrahedral symmetries. This is A4. So here, the group A4 is a different subgroup of S4. So this A4 is equal to the symmetries of a tetrahedron. And that is also a subgroup of S4. It's probably the largest subgroup of S4, I think. And this guy's a little bit tinier, and it doesn't sit in here, and it kind of straddles over the 2 of them. So if you were to take S4, and we're gonna see this together. If you were to take S4, and then over here you got A4, and over here you've got your odds, then D4 kind of sits in the middle there and shares a little bit of each. It's much smaller. Yes, sir?
Does it share an even amount, like on each side?
Yes, yes. In fact, so that's a cool result. Yeah, good intuition. Any subgroup of, and I think I'll probably maybe prove this at some other point, but if you have any subgroup G of S sub n, then it's either all even or exactly half even. As soon as you have 1 odd, you've got half of it being odd. And the proof of that's kind of like that map that I sent up before, that you can make a 1-to-1 correspondence using the only odd you know about. Yeah. Yes, sir.
Is like the half even, half odd thing gonna be because like all of your reflections are odd, in that they're just like
Yeah.
transpositions, and then your rotations plus the identity
That's right.
are all even.
Yeah.
Okay.
Yeah, good, yeah, check this out. If you were to convert this into product of transpositions, it would be 1, 3, 1, 2. So that's even, odd, and that's even. So yeah, you're right. I think that's how it works out.
Okay. If you like were to consider the identity a rotation, could you make a blanket statement that for any one of these like permutation groups, like there's as many rotations as there are reflections?
Yes, I think so, yeah. And we're gonna do this in a really cool way. We're gonna build this in the way that you really are over my house. We're drinking beer on the sofa, or whatever you want.
Non-marshmallow beer.
Not marshmallow beer, definitely. How about a pale ale, maybe, something like that, or lager, you know. Or tea, I've got shitloads of tea, as you know. What is this? Who is that, man? So let's think about this thing, and let's understand this group completely. And we're gonna set it up, and I don't think we're gonna be able to complete this. Oh God, no. A, B, C, D. So there's my square. Let's set up some things. And maybe you could work on this a little between now and Wednesday. I'm gonna set you up. This is like a fun thing. So go do what you do, beer, whatever. You go do your thing, whatever that is, and work on this. Not to turn in, but to discuss, and for your own pleasure. That's right. So our identity is don't touch anything. Cool, leave the square as a square. So which way do you want to rotate? Let's make these numbers. What am I doing? 1, 2, 3, 4, sorry. We could use letters, but what do you want the rotation to be of 90 degrees?
Clockwise.
Which way? Clockwise?
Clockwise.
Clockwise. So we're gonna set, which works good because then 1 goes to 2. So 1, 2, 3, 4. Awesome. Cool. Can you crank out the other row squared and row cubed, please? And we're gonna do something really different here, and that's gonna be the fun part. So after we crank these out, oh wow, does this actually break into 2 transpositions?
Yeah.
Yeah, that's so cool. That's cool. Yeah, that's so neat.